This video is going to show you how to do calculations for a titration between a weak base and a strong acid. But first, I want to review something we went over with you in class. When you're doing titrations, the first thing you have to do is you have to identify the strength of the acid and the base. So if it's strong base and strong acid, it's stoichiometry only. And that's not what we're going to be doing in these problems. We are going to be doing a weak base and a strong acid. So this is really a buffer problem. What we're going to do here is we do our stoichiometry first, and then we do our equilibrium or ice chart next. So I'm going to go and start the problem. Okay, so here we've got 100 milliliters of 0.050 molar ammonia. Kb is given. We're titrating it with 0.10 molar HCl. Okay, so what you want to do, you know it's a titration. You have ammonia, which is a weak base. That is confirmed by the fact that it has a Kb. And then you are mixing that with 0.1 molar HCl. If you think about the rules that just went over with you, when it's weak and strong, you have a buffer problem. The very first thing you're going to do is stoichiometry. And then you're doing equilibrium next. And if we have 0 milliliters of strong acid added, it's just an ice chart. So let's go back and look at that. Okay, so we have 0 milliliters of HCl added. The step said it's just an ice chart. So you take the ammonia plus water. That's going to be in equilibrium. The weak base accepts a proton, becomes ammonium, produces hydroxide ion, confirming that it's a base. So we set up an ice chart, draw the fence, X out water because it's a pure liquid, substitute in our molarity of ammonia because that's all that's there. The 100 milliliters doesn't matter. There's no ammonium and no hydroxide. We know our Kb, so we can do product side goes up by X, reactant side goes down by X. We get 0.050 minus X, X, and X. So in our expression, Kb is equal to 1.8 times 10 to the negative fifth. That's equal to X squared divided by 0.050 minus X. If we take Kb times 100, we will get 0.0018. 1, 2, 3, yep. So this concentration, this is still lower than our initial concentration, so we can approximate. So we will take, we'll do math now. So we're taking 1.8 times 10 to the negative fifth times 0.050, and we get 1.44 times 10 to the negative sixth. That is equal to X squared. We will take the square root of both sides. And when we do that, our X is 0.0012. That is our concentration of hydroxide ion. So in order to get pH, we will need to find hydrogen ion concentration. So to get that, we will do 1.0 times 10 to the negative 14th divided by 0.0012. And we get 8.3, how many sig figs? 2, so 2 sig figs times 10 to the negative 12th molar. We will need to do, to get pH, we do negative log of that number. Sorry, I ran out of room there. And our pH is equal to 11.08. Okay, so now we're going to add some weak acid. So I guess we can add 10 milliliters. So we want to look at our rules now. We are told that if we have weak plus strong, it is a buffer problem. We are going to do stoichiometry first, and then here it tells us that we have a common ion problem as long as some of the weak remains. So we're setting up an ice chart, and we can do an equilibrium problem or use Henderson-Hasselbalch. Now this is because we can do this before the equivalence point. And that's where we're going to be. So let's go back to this problem. And now let's say that we've got 10 milliliters of HCl. Okay, now we need to remember that this is the equilibrium to which that HCl is being added. So strong acid is going to react with the weak base. So we start with an initial change final table. Strong acid is HCl. Weak base is ammonium. And this one's a little weird because this is kind of like ammonium hydroxide. So we end up getting ammonium chloride. Now, the chloride ion is the conjugate of a strong acid, and so it's a weaker base than water, so we just ignore it. So what we will do is fill in what we know. Because this is a chemical reaction, we have to go to moles. So we had, let's go ahead with our HCl. We have 10 milliliters of HCl, and we need to go to millimoles. And our HCl was 0.1. So 10 times 0.1 gives us 1 millimole. We have 0 millimoles of ammonium to start. Now, ammonia from the previous slide, we have 100 milliliters of ammonia, and it is 0.050 molarity. So if we take 100 times 0.050, we are going to get 5 millimoles. Now, just like when we did the weak acid strong base problems, we look on the reactant side to see what's limiting. The strong acid is limiting, so the reactant side goes down by 1 millimole, product side goes up by 1 millimole. We have no acid left. We have 4 millimoles of ammonia, and we have 1 millimole of the conjugate acid. So what we want to do with these is we've now got 110 milliliters, and we want to go from millimoles to molarity. So this is 0.036 molar, and 1 divided by 110 is 0.0091 molar. Okay, now this is before the equivalence point, so we don't have any acid left. So we can use, this is our stoichiometry part. That is done. So now what we are doing is we're going to use the equilibrium part. I'm going to go to a different slide for that. So I'm going to rewrite that equilibrium. Ammonia plus water in equilibrium with ammonium and hydroxide ion. So now we're setting up an ice chart. Water I'm not including. If I go back, all right, I've lost it. Sorry. If we go back and look at my previous slide, I have 0.036 molar ammonia and 0.0091 molar ammonium. So let's put that into our table. So we have 0.036 molar ammonia, 0.0091 ammonium, and no hydroxide. Now, I have a choice. I can do an ice chart. If I were doing that, Product side would go up by X, reactant side down by X. I'd get 0.036 minus X, 0.0091 plus X, and X. However, because I have the weak base and its conjugate acid, I can use Henderson-Hasselbalch. So I'm going to use the POH version, which is the negative log of Kb plus the concentration of the conjugate acid divided by, whoops, this is log, I always forget that. The log of the concentration of the conjugate acid divided by the concentration of the conjugate base. Not the conjugate base, the regular base, sorry. So I don't know POH. I want to do negative log of 1.8 times 10 to the negative fifth plus the log of the conjugate acid concentration, 0.0091 divided by the base concentration, 0.036. Our POH, when we do that, is 5.34. And then to get pH, we do 14 minus that number, which gives us 8.66. Okay, so I'm looking at this number and I'm thinking this does not look right because I only added 10 milliliters and this wouldn't be a lot of buffering if I started at 11.08. So I need to go back and check my setup. Well, I did that. Everything is right, and then I checked my calculator. And when I checked my calculator, I realized I did not do the log of this ratio. I just did the negative log of 1.8 times 10 to the negative fifth plus this ratio. So when I went back and I recalculated, I got a POH of 4.14, which means we are taking 14 minus 4.14, which gives us a pH of 9.86, and that is much more reasonable. So I'm sorry you had to watch me correct that. Okay, so now what we're going to do is continue. We're going to go and we're going to add 25 milliliters this time. So let's go back. Go away. Let's go back to this slide. And so now instead of 10 milliliters of HCl, we are going to have 25 milliliters of HCl. Now our amount of ammonia did not change. Our strong acid, HCl, is going to be added to this buffer. The strong acid reacts with the weak base. So, because it's a chemical reaction, I need to find moles. So I'm going to use 25 milliliters times my molarity. The molarity of the HCl was 0.1, so this gives us 2.5 millimoles. So if I look at what I've got here, I need to get rid of all this because we have a different amount now. Okay. I have half as much strong acid as I do base. So I am at the halfway point. If you remember that from the weak acid, strong base slide. Now, what's true at the halfway point is that pH equals pKa. Or in this situation, POH is going to equal pKb. Now, if you remembered that, you could just go ahead and state at the halfway point, because I have half as much strong acid added as I do weak base, and so this relationship is true, and save myself a lot of work. More than likely, we're not going to recognize that, so we're going to say, okay, HCl is limiting, so the reactant side will go down by negative 2.5. product side would go up by plus 2.5. No HCl left. I have 2.5 millimoles of ammonia left, and I have 2.5 millimoles of ammonium formed. So now I can go ahead. I've got 125 milliliters. Now, hopefully you're seeing that doesn't matter which one I do, I'm going to get the same molarity. So I'm just going to write it once. It's 0.020 molar. Okay, so if I go on to the next slide, and I need to get rid of what I've done here, because we don't need that. We did that already. Okay, so if I think about what I have 0.020 molar and 0.020 molar. No hydroxide. So I could use Henderson-Hasselbalch. I could do an ice chart. I can do either. Doesn't matter. Henderson-Hasselbalch is faster, so I'm going to go ahead and do that. I'm going to substitute these two values into Henderson-Hasselbalch. When I do that, I realize that this ratio is 1, and the log of 1 is 0. So POH is going to be equal to just this here will be 0, so I'm really just going to get rid of it. Okay, so POH is equal to the negative log of 1.8 times 10 to the negative 5th, which is 4.74. So our pH is 14 minus 4.74. So that gives us 9.26. All right, so I'm going to do what I did last time. I am stopping before the equivalence point. So if I go back and think about what we've talked about here, prior to the equivalence point, I can use Henderson-Hasselbalch. Remember that when I have no strong acid or strong base added, all I do is stoichiometry. So I'm going to do a second video where I start at the equivalence point. So I will be starting here in the next video.